Hello everyone, so I am Calin and this is my coworker Roland, and we are working at Google as software engineers, and we are developing the Art Android Runtime. And our sub-team basically it's about developing the compiler for the Android. And yeah, we are here to present you our new shiny compiler which will ship in the next version of M. And this talk will be pretty high level, so we'll not get into very deep technical stuff, but if you have any questions, feel free to interrupt either during the presentation or you can ask them after. And yeah, let's start. So just a quick overview of what we will be discussing. How many of you here are familiar with Android Runtime? 1, 2, 3. Half of them, okay. So I'll also give you a brief introduction and a bit of history over what we do what the Art Runtime is doing in Android and how we came to develop it. And then we'll move to the compiler part. How many of you are familiar with compilations, with compilers? So it's good that it's not too technical then. So I will basically motivate why we developed the first compiler and why we needed to improve and develop a new compiler for the Android. And obviously the answer is always make things faster. And we'll talk a bit about the results, what we have so far, and what is our future work plan. Okay? Okay, so the main question is what is art, and as you can see in this picture, I hope you can I can induce into you the artistic nature of software development, but I will not try to answer exactly what is an art because it's mostly for critics, and I will try mostly to approach what is that small box there is Android is upgrading for your phone. Many of you probably seen that before. It's a bit, it takes a bit of time, but I promise that it will make your phone faster. And basically what my team is doing is responsible for you to show that box. Not the UI level, but whatever is happening behind the scenes. And here's the full stack of what's happening in Android. It basically have the kernel and the drivers, the OS on top of it, and then we basically are the core of the stack. Is there any pointer around? A pointer? No, no pointer. Okay.
I think you can use the mouse here.
Yeah, so basically we are in the middle of the stack, and we are the bridge between system UI and platform and everything that the OS does for you. And to illustrate this in a bit more simplistic way, we are that golden man sustaining the entire Android platform and ecosystem, which is like 1 billion apps, 1 billion devices, more than 1 million apps. And we link it with the drivers, and we make your app actually running. So I like to think that we are at the core of Android, but of course there are other components without which Android wouldn't be able to function properly. And let's talk a bit about a brief history. And Art was developed as an evolution of the previous runtime, which was called Dalvik, and it had a KitKat development preview, and we completely replaced the old runtime in Android 5.0 in Lollipop. And what it does, it basically runs your apps, your APKs, and translate them to the native code for the CPU, obviously, to run them. And it comprises of a ahead-of-time compilation and an interpreter, and I'll talk a bit later about it. It supports all common backends, starting from ARM, MIPS, MIPS64, and so on. And it's completely developed in public space. So if you go to Android open source project, there is an URL there. You can see all the commits, everything that it's been done in the runtime. So we're pretty transparent about this. If you have ideas, contribution, you are welcome to hear about them. And to move forward, so this is okay. So this is roughly how the evolution works. So initially, Dalvik had just an interpreter, and it has a tracing JIT compiler. Anyone familiar with JIT or doesn't know what a JIT is? So just to sum things up, so the JIT compiler detects hotspots in your application and will compile the trace. So next time you re-enter the execution of that particular sequence of code, you'll have a much version of it, and you'll not need to a much faster version of it, and you'll not need to interpret it. And yeah, it will improve the overall running experience. And the apps were optimized during the installation and the upgrade. And when I say optimized here, basically we'll transform the DEX code into a more friendly version for what it was there, the interpreter. And it only had 32-bit support. And this was designed in the early stages of Android. So when phones were used to have 60K amount of RAM and low CPUs, and as you know now, phones are pretty powerful, so it didn't scale quite up. So the team decided back then that it's time to change the runtime, and they come up with ART. And we decided that an ahead-of-time compilation, basically, which will take your DEX code, compile it, and that's it. You don't have to interpret it anymore. It's much better for Android than the previous JIT. And the apps were compiled during the installation and upgrade time. That means that obviously the installation time is a bit longer, but hopefully it runs faster. And they did run faster. We added 64-bit support in Android in ART, and we improved on garbage collector, thread locking, and concurrency model. And we basically managed to do that keeping the same DEX bytecode, so we didn't have to extend anything of that. So for developers, that was quite I would say, smooth transition with some quirks every now and then, but that's always the case. So if we think from a developer's perspective, is what's happening in the Android runtime is basically we have the developer environment, and that the developers usually use the Java language to develop applications for Android, and that gets compiled to an intermediate representation, a form of bytecode, and that's basically the APK that will be on the Android device when at the installation time. And how the code gets from Java to DEX is either the Java toolchain and then with DX, or with the JEC compiler, which is now able to go directly without passing through the Java toolchain. And on the Android device, when we get the APK, basically we run that through our own compilation, and that the blue box there is actually what my team is doing, and that's the main focus of this talk. And we'll transform it into an OAT file, which is more or less an ELF file. And then we run it. And the OAT file contains all the native code that is needed, and metadata and so on. And yeah, so let's expand a bit on the blue box and see what's there, and talk a bit more about what is that actually that we compile. So the DEX format is a register machine, basically. It has around 65K of virtual registers, and it's hardware agnostic. Most of the instructions are 60-bit units, and sometimes they are confusing for a compiler, and that trigger a lot of challenges. One in particular is that, for example, it's not easy to distinguish between longs and doubles, and if you want to optimize for that, you will need to do extra type inference at that point. So here is where the compiler work gets a bit more tricky. And then the DEX file gets run to the dex2oat, which is the Android compiler, and produces an OAT file. And the OAT file contains the native code. We also store the original DEX code, and I'll talk about that in a minute. And it also has some metadata for the runtime, and that metadata is basically points to know for example, for the garbage collector to know which objects to collect, or for debugging purposes and so on. And all this is a standard ELF format. And you may wonder why we keep the DEX code. Well, sometimes we want to de-optimize things, for example, when you debug, and then you want to jump back to the interpreter. So you have to know what you need to interpret. So this is one of the reasons why we keep the DEX code around, but not the only one. In terms of the compiler, we have two compilers. Quick compiler is the first compiler. I'll talk a bit about it. And the new compiler is called Optimizing, and it produces faster code. It's not faster yet in terms of compilation time, but we'll get to that. And the compilation unit for all this is the Java method. So we don't compile all the class or no. It's just the per method, and we do that in parallel. Okay, so let's see a bit what the quick compiler does, and I also motivate some drawbacks that made us develop a new compiler. In terms of the pipeline, it's the usual stuff that you would expect from the compiler. You have the DEX file, which is the bytecode. We transform that into a mid-level intermediate representation. We run some optimization on them, then we move forward to even a lower intermediate representation, which is much closer to the native code, and then we eventually produce native code based on what you have. There are various degrees of optimization that we can perform on the two IRs, but one of the drawbacks that it's easy to explain on this diagram is that we can't share optimization between the two IRs. So extending the current optimization or adding new optimization, which will need to be run on both representation is quite hard. And that's one of the reasons that we develop a new compiler. In a bit more detail, the quick compiler is actually based on the previous JIT that was in Dalvik. So that was a tracing JIT. We adapted it to work at the method level and produce native code. So it was designed mainly on speed because a JIT needs to be fast, and the optimizations were not the main purpose of it. And it was not really easy to extend or to add new optimization, particularly because of the two different IR levels, which are quite different between themselves. And in terms of optimization, that actually were luck and kind of made the performance suffer was we didn't have register allocation. Not a real one. We had some register promotion and such. And you didn't have any inlining, and other fancy optimizations were pretty hard to add. So when we try to scale this and we try to add more and more and to make the code faster, we realize that it takes too much time to extend quick and to add things on top of it. So it's much better if we try to create a better infrastructure for optimization. So not only to make code run faster, but something that is extensible, something that is easy for example, for partners to work with, and it's much more friendly for extensibility. And my colleague Roland will present you what we are doing in optimizing to address this and how we actually make things faster.
Thanks. So optimizing is a solution to address the issues that Calin talked to you about the quick compiler. We had this goal in mind when we designed the optimizing compiler. Of course, the first goal is to make Android run faster. With the art, we had already a very good improvement regarding speed execution of applications. But we knew we could do better by adding new optimizations in the pipeline. And this is one of the goals of optimizing. The second goal was to overcome Quick's limitations regarding software engineering and extensibility. And more specifically, make it easier for the developers and contributors to add optimizations to the pipeline. So the work on optimizing started last year. So the compiler is almost 1.5 years old. It's driven by the Google Art team, mostly in London and in Mountain View. And we have integrated a lot of contributions from partners, which is a very good thing because it shows that it's a very good ecosystem. And this is one of the strengths of the Android platform, where through open source we can integrate contributions from many partners. All the work is done in the open source project, Android open source project, which is quite convenient because it makes integration and testing very faster and easier. And the compiler is able to compile 1.5 million apps, but it's an old number, maybe it's probably bigger now, from the Play Store. And thanks to Calin, we have an infrastructure to test that at scale. So this is the rough pipeline of the optimizing compiler. So of course, we have the same input and outputs. And the biggest difference is that in the middle, we have a single high-level intermediate representation, which is So we have we have one box here. Even if we have two boxes, this is the same intermediate representation. We start by building a control flow graph from the DEX file instructions, and as soon as we have it, we turn it, into an SSA form, static single assignment form, which is extremely convenient to implement optimizations. All the optimizations are done on this form, on this representation. And once we have optimized the code, we proceed to a liveness analysis and register location, and we generate code directly from this SSA form. We have many generic optimizations. I will talk a bit more about this in a few minutes. And also, we're starting to have a few architecture-specific optimizations because the framework is quite extensible. And I think Alexandre will talk about that just after. We target the same architectures, and we almost have the same support. MIPS is done yet. And for ARM64, the backend was contributed by Linaro using Vixel, and it fitted quite nicely into the design. So this is the design of the optimizing compiler, a unique central high-level representation, which makes it easier to apply optimizations at different levels in the pipelines. So even if we have different optimizations, sometimes we want to rerun them later. For instance, we have a simplifier which tries to apply arithmetic simplifications, and sometimes we replay it because we know that the previous optimization may have simplified the graph enough so that it's interesting to replay again the simplification. The pipeline is extremely clean, which means that if you look at the code, I think it's maybe 20 or 30 lines of code, the pipeline, and it's easy to interchange the different passes so that we can experiment with different optimization schemes and add new ones quite easily. Every optimization is a block, which means that they can be interchanged very easily, and they produce information as they run, so that we can use them to debug and test the compiler itself. By its very generic nature, the compiler supports Arch-specific optimizations, and they're implemented exactly the same way because we have a single representation, intermediate representation. So even extra nodes, extra instructions to the control flow graph are implemented in terms of the same data structures. And at the end, we have 6 backends generating code directly from this control flow graph in a SSA form. So the intermediate representation is quite classic. It's made of basic blocks linked by control flows, so go-tos and conditional jumps and so on. In SSA form, of course, we have the properties that every variable is only assigned once, which makes optimizations easier to implement. This representation is highly reusable, so we can use the same canvas, the same tools to implement optimizations. The transformation to SSA comes with the recognition of loops, which is, of course, quite useful to implement optimizations. Every time we apply a transformation to the graph, we have the possibility to dump information using the C1 visualizer format. And this is quite convenient because we can use it to debug the compiler and also to test it. For instance, I'll show you later how to test it. So here a non-exhaustive list of optimizations we have in the compiler. They're quite classic, but they're very efficient, effective. The biggest difference with Quick, I think, is probably inlining, because Quick didn't have proper inlining. It showed a dramatic improvements in some benchmarks. And the second one is probably the register locator. The fact that Quick didn't have proper register location forced it to spill many DEX registers to the stack, which is quite inefficient. Yeah, and also in addition to the possibility to dump information to the C1 visualizer format, we can record statistics during compilation, which is useful again to debug, have statistics over the compiler. Okay, so this is an example of the test, a real example of tests that we write with a tool that is called Checker, which uses the intermediate representation. So we write the tools directly in a high-level form in the Java programming language, and we add annotations in comments here made of different assertions that can check, for instance, that the graph has a certain form before constant folding, constant propagation, and after. And we see that after we have removed this instruction. And so we return immediately the constant because we were able to propagate the constant from x to the definition of y. So this is very simple, but in practice, this is extremely useful because we use it to, of course, prevent regressions in the compiler and detect undefined behaviors and non-deterministic behaviors. Also, it's very useful to set up the optimization when we write them, because as we implement them and design them, we can see exactly with test how the compiler is behaving. I will conclude with on the optimizing compiler, the design of the optimizing compiler with this part, which is about metadata we add into the runtime. So Calin said that the old file contains not only DEX code, but only native code produced by the compiler, but also metadata that we call stack maps, which are associated to different points or safe points in the code. So this information is useful in the case of checks like null pointer checks, array bound checks, when we load a class or a string, when we call the entry points of the runtime, when we de-optimize, that is when we go to the interpreter, when the garbage collector has to run and has to know which variables are references that may be traversed and collected, for the debugger as well, and more recently for implementing try-catch, where we communicate with we play with the runtime to get the live variables and restore them. So the idea was to add to the generated code stack maps and record information such as the mapping between the native PC, the position in the native code, and the DEX PC, which is the position in the DEX code, the original code. Sorry. We also record which DEX registers are instances that may be collected by the garbage collector, so either in physical registers or in stack slots. And we also record the location of DEX registers. This is useful for example, when we call when we need to know whether DEX registers has been implemented as a constant, as a pair of registers, or as a stack slot. And to support inlining and debugging, we have inlining information as well, because of course the code produced by the native compiler, the native code produced by compiler, can be quite far from the original code, so we have to map information from the original methods in the DEX format. This format is binary format stored in the old file, and it has been designed and improved to be as compact as possible. We still have some work to do there because this is quite a big part in the old file, and we're going to work a bit more on this. I will present some results from the compiler, and Calin will give a conclusion and analysis of what we discovered. So here's a list of benchmarks to the aggregated numbers. For instance, the MISC benchmark here contains benchmarks such as LinPack or ChessBench. The Suites benchmark here contains benchmarks such as binary trees, Mandelbrot, and so on. In most cases, optimizing is able to outperform Quick. Sometimes we don't do as well. We think that most of the issues are, for instance, related to the absence of instruction scheduling in the compiler, which Quick has, and we're working on it. All of these numbers have been produced from our tools, internal tools, from a code base dating from a few days ago. So that's for runtime performance of the code. Regarding code size and compile times, we don't do as well. So we have quite a slight increase compared to Quick, especially on ARM 32-bit code. And the compiler is between 20 and 25% slower than Quick when we compile. So this has an impact when people update their phones or install applications. And we are working on both those areas. Those numbers have been produced by running the compiler on Google Play Services, Google Docs, Android Framework, and we have, of course, other applications and code base that we use to assess the quality of the compiler. And with that, I'm going to hand it over to Calin, who will analyze these numbers.
Okay. Back to me. So I'll finish with some status, and we'll see what is one of the criticisms that we make ourselves towards the compiler, and probably could see from the results that one of the benefits, we definitely generate faster code for most of the benchmarks, and overall the Android performs faster. We do have a much cleaner design, and it's pretty easy to extend and add new optimization, new backends, and so on. But as you've seen in the last slide, there are some areas that we work to improve. Obviously, if you want to have better code, you need to perform more optimizations, and those optimizations take time. So you have longer compile times. That doesn't necessarily need to be the case, or at least the difference can be smaller. So we are still working in making that more efficient and reducing compilation times. We do generate more code, and that should not necessarily be the case, but it's a bit expected. And we are also working on reducing that, and have some exact points that you want to tackle in the near future. And the compiler actually the optimizing compiler doesn't handle all the text patterns. So the current version that will ship in the next release of Android, for example, doesn't compile methods with try-catch. But we actually had that supported already in the Android open source project, which is like the edge repository of Android. And whenever we don't support something, we use the previous compiler, or we fall back to the interpreter, depending on what's the case. And yeah, as I mentioned, the current status is optimizing will ship in the next version of Android, and all the apps will be compiled. And the only thing that will still be compiled with the previous compiler is the Android framework. And the main cause for that is we didn't have time to add a few optimizations that the framework quite benefit of, and there are some debugging issues with the framework that we wanted to address before enable compilation of it. We do have a lot working in AOSP already, so there is we already addressed more DEX code patterns, like I said, the try-catch issues, and we have support for a new garbage collection algorithm, and we're working on induction variable analysis, load store elimination, and more optimizations to come. And I will just conclude with the points that we are working to address in the in the upcoming months. So that's mainly improving generated code size, compilation time, and adding more optimization. In particular, we are working now to have more architecture-specific optimization, and Alexander will talk about this in the next talk. And yeah, having said that, I thank you all for your presence. And if you want to know more, you can go to these links. The first one is the public documentation. The first one is the public documentation of how Art and Android Runtime works in general about the compilers. And the second one is the repository for the AOSP. And you can check it out and see what we do every day. Thank you. Any questions? I have some mics to hand around if there are any.
This one is number 2, so I guess this one is number 1.
One, two. Yeah, great.
So 2 questions. First is, you said the quick one has 2 IRs, different IRs, and the optimizing only has 1.
Yeah.
In LLVM, we only have 1, and there's always people asking to add different levels of IR so they can do clever stuff that our IR can't. And I want to understand why you moved from 2 to 1, because I believe the 1 is the best answer, but I want to know from you guys what made you choose to go back to 1 instead of having 2.
Well, I think I think there's a slight difference with the LLVM, which is quite general, and the compiler has to run on devices. And I think this is also the general design of the optimizing compiler is to have something simple. Sometimes where we could have something very sophisticated, we decide to go for the simplest solution. So I think in this case, 1 IR was a better option. I think if we were to implement something for in a much more general context like a Clang or GCC, we would probably go to we could possibly have several levels of ARs. Yeah.
Okay, so it's more like, was it compile time or just simplicity and code size of the compiler itself?
Yeah. I would say simplicity is one of them. Is the main benefit, and reusing and having just 1 IR to implement all your optimizations make it much more easy to reason about them, and you don't have to think about sharing between different IRs if you want to borrow results.
And the mapping between might not always be bijective, so you kind of lose information while moving through, and then you can't optimize. Yeah, because the problem is, a few years ago I had a talk with Adobe, and they said they had 5 different JITs. And even running all 5 with completely different IRs, completely different optimization levels, etc., it was still smaller code size, lower memory footprint, and faster than trying to run LLVM IR on the same ARM machine.
Yeah.
Right? Of course, okay, that was like 5 years ago. But the question, what I thought is that because they had 5 different IRs and 5 specific IRs for the specific jobs, it was a simpler job to have 5 than to have 1. And now you're saying that in an ARM chip, for Android, for all these loads of apps, having 1 is better code size, better, simplicity and stuff. So I think that's a good thing for me that, you guys are actually proving something that I believed it was right, but I only had proof of the opposite, right? So, okay, that's a good thing.
Well, despite the fact we still have a lot of optimizations, but we probably don't have a full-scale range of optimizations from a compiler like Clang or GCC. So that's also I think a reason why we didn't want to have more than 1 AR.
Right, yeah. So about the pipeline, you said something also interesting that I'm trying to do with LLVM and I failed, is, no, it's a bit before, but it doesn't matter.
Yeah.
You say that you have like one simple pipeline that you can actually add and remove optimizations and maybe even swap the order or etc., right? In LLVM, every time I try to take one out or put one in between, you know, sometimes I get even seg faults. That was 2 years ago, so it's been better now. But, you know, it's not a simple thing to add and remove passes. Do you guys have the same problems? Because, like, the patterns just dissolve, right?
So it really depends on the passes that you're talking. Obviously, there are dependencies. For example, if you perform loop code motion, invariant code motion, you would need side effect analysis and such. So with respect to dependencies, they are hard constrained, but in many cases, we try to develop the analysis to be resilient. If one is not there, then we can still run it. Right. So for example, for inlining, obviously, if you have a reference type propagation and you know the types of objects, you can do better inlining, but you can still do inlining without reference type propagation, so without having very precise types.
Right.
So in that respect, we have, I think we are doing pretty well in isolating one analysis from the others, but we do have our dependencies.
Yeah, sure. But do you guys do these tests where you do like random removal and addition, you know, or move on the pipeline?
We don't do it, I mean, actively, like we don't have
This is
a
not
test,
something,
a test like, hey, swap these two analyses and see if that works. We do that like integration tests and usually regression. So when we swap, we rerun all the tests and we see that it's still good, but we don't have anything that stress tests that if we swap two optimizations, it will work.
Like a genetic algorithm that will find the best order or...
Yeah. No, we don't. I mean, that's usually mostly on our personal analysis and expertise that we think it's better to run in this order.
Okay.
Yeah, the compiler is not meant to be configurable, like deciding from the command line which optimization and in which order you want to perform them.
So you don't have like, 1, 2, 3, you just have one optimization level?
Yes.
Right. We do have some filters for different devices when you know that, for example, compile time is an issue or generated code size is an issue. But it's nothing very extensive, like it's fairly simple.
So you talk about compile time, but if I got it right, it runs on the initialization, right? When you like update Android, it says optimizing apps. That's what it is, right?
Yes.
Which means the compile time is only a problem when you update Android, say, once every 3 months. Yeah. But for the rest, you don't really care much. So you shouldn't, because the other thing you say is that some of the bits you can't compile, so you just leave it as Java class, whatever, that it runs on the VM. Couldn't you try to, so why can't you compile this? Is just like the compiler's not good enough yet, or you don't have like some runtime information that you need?
So one example is we are still developing optimizing, so we don't have a full coverage of all the patterns. And that's one thing that for which we don't compile methods. For example, we didn't have support for try-catch because you'd be surprised that only, I think, just a few % of the Java methods actually use try-catch. I was quite surprised about when I performed the analysis. So that's one case. The other case, for example, you have a huge method, for example, a class initialization, which you know you run just once, it doesn't work compiling and wasting time because it's...
And it's okay because you only run it once every time you start the app.
Yeah, exactly. So why we are still trying to reduce compile time, obviously when you install an app, like a big app, like a 200 megabytes app, it still takes time. And obviously for the user experience, it's much better if we can do that as fast as possible. Usually the network time and all the other aspects takes much longer, but we are still trying to do our best on our side.
Mm-hmm. Okay.
Oh, yeah, because the compiler runs as well during installation of apps, when you update the apps. So it depends.
So every Play Store update is going to run again.
Yes.
Yeah, it makes sense.
So well, I think it's not as bad because it's only one app each time.
Or
so,
sometimes you just forget and then you have like update 16 apps.
Yes.
Yeah. Okay. Thanks. Anyone else?
Any more questions? Okay.
There's a question.
Yeah. Okay, so you talk about the compilation time, And I work on a smartphone, and it really matters. And because we see some application during its initialization time, you will download some private jar. And so if you download jar, so this comparison will run. And it will take very long time for some applications, so it really matters. So I'm thinking that if you guys can move some of the optimization time from the DEX to OAT into the Java to the DEX time, so that the optimization time can be shorter.
So
Is that possible?
So yeah, you mean so moving some of the work upstream in the compiling when we compile the source Java source to DEX.
Yeah. But maybe you need a different form from the DEX, so that it will already some of the optimization work has already been done in the.
You guys, you said that you can control code size and compilation optimization stuff. What if, when you install the app, you run the fastest compile time you can possibly get and install the app in a corner that is not optimized, but it can run?
Yeah.
And then when the phone is idle, you just recompile again with the best optimizations you can get.
Yeah, that's definitely an option. The main question is there, what do you do when if the user launches for the first time? It will have a crappy user experience.
Is it that bad? I mean,
we'll have to experiment
you said
more.
25%. I think that's acceptable.
There's something for the benchmark.
Yes.
Yeah.
But benchmarks are normally bigger the difference.
Different apps is different.
Yeah, no, but most of the time you see a bigger difference in the benchmark than you see in real world code.
Yeah, it's completely.
So, you know, if you
It-
get only 25 difference in the benchmark, you're going to get 5.
Can get more data.
It really depends on apps, and when we say 25%, it's again it's an average.
Yeah.
Some apps can go like 50% more
Did you
more
get
time.
like height, like more than 100, more than twice?
We do have like 200% on some benchmarks, like
Yeah.
even more.
Yeah, okay.
But it's more interesting than to show the peaks, to show the average, because
Yeah.
you always have peaks, and it's very interesting in doing better in all the aspects, not just on several benchmarks.
I guess you guys get most of the big stick for different apps. You know, for example, the apps never change. When you update the framework, you optimize again. You should get all the statistics of all the methods you compile. You
Yeah.
only compile those work.
Yeah, that's what we are trying to do. I mean, we do have some heuristics about what words being compiled, and obviously you can do better and you can experiment more. And
Also, this most of the time, all the optimizations usually code in user time for the apps, not necessary. So you should design, you know, if you compile method they get that long, but actually the benefit is very small. Then
Yeah.
you should get rid of this optimization next time.
yeah,
Well, but you know what code is hot and cold before you actually execute the app.
That's why the first time is the worst time.
Yeah.
But later on, when you,
So
for
that-
example, you update into OTA, but also apps, OS.
Yeah.
So then you really become, for example, the phone OTA, like OTA, the framework change, and then oh my god, you 200 and then
Yeah.
10 minutes, the user will float the phone.
Yeah.
fortunately that happens pretty rare.
Yeah. For,
That's so.
Yeah.
And also the whole worst thing is that the desktop is crazy, driving the CPU hot. I can shut down the phone. Oh my god.
well, this is a per device issue. So
I think desktop is really number of
Well, compilation usually it's quite expensive, and this is why we are not doing it when we are running other services, or if when you install an app, we will not use all your cores and such.
That's why I said OTA is the worst. Upgrade, and especially, I think in Google side, the latest phone is okay because not many versions. In the Far East, I tell you what, OTA
working on it.
Any more questions?
Okay, and thanks again
Thank you very much.